Hey guys, it's Mr. McHugh again, bringing you another video on the properties of trigonometric functions. And the essential question for this one is, what are the relationships between a right triangle and circular definitions of the trigonometric function? So we've seen these trig functions, sine, cosine, tangent, secant, cosecant, cotangent, in the context of right triangles. But this video is going to concentrate on those angles in the context of a coordinate plane, and you'll see what we call the circular definitions of those functions appear in the context of the coordinate plane. So here's our coordinate plane, and an angle is in standard position in the coordinate plane if its vertex is the origin and its initial side is the positive x-axis. So this initial side, there's two sides to an angle. The positive x-axis creates the initial side, and if we draw the other side of the angle from the origin, draw it like this, we can see that we've created the vertex of the angle at the origin, and this second side we call the terminal side of the angle. And we'll give the angle the name theta. It's typical for an angle. We'll give the angle theta, and that theta is in standard position because its initial side is the positive x-axis. Now, one of the benefits to looking at angles and trig functions of angles in the context of coordinate plane as opposed to the right triangle is the size of the angles that we can use. If we think about right triangles, what size of angles work in a right triangle context? Well, if one of the angles is the right angle, 90 degrees, then the other two angles have to be less than 90 degrees. So in the context of right triangles, angles have to be, and if I use theta for my angle, have to be less than 90 degrees, or pi over 2 if we're talking radians. We can't talk about right triangles with angles that are larger than 90 degrees or pi over 2. But in the coordinate plane, if we think about the circular definition of these angles, those angles that are less than 90 degrees are just the angles in this first quadrant, which I drew earlier, that theta I drew earlier. But we can also extend angles into the second quadrant, and an angle that's in standard position that extends into the second quadrant might look like this. Here's the initial side, and here is the terminal side, and you've got an obtuse angle here that extends into the second quadrant. We never could have drawn that angle in the context of a right triangle. We can extend angles into the third quadrant down here, and an angle that looks like that extends into the third quadrant might look something like this. And now this angle extends beyond even 180 degrees, beyond pi radians, into the third quadrant, and of course we can do that for the fourth quadrant as well. And the circular definition of angles gives us a much broader range of angles than right triangles do. And here's another way of seeing the broad range of angles we can create in a circular coordinate plane context. And one way is to look at what we call coterminal angles. These are two angles that have the same initial side, which in standard position we'll talk about the initial side being the positive x-axis, and the same terminal side, clear that stroke, and the same terminal side, we'll draw it maybe over here, but the angles have different measures. So if we call this angle right here angle theta, how is it possible to take the same initial side and same terminal side and have an angle other than theta? Well, a couple different ways. The first is, if I draw my angle in standard position with the initial side the same, but I don't stop at the terminal side the first time, I can draw an angle that goes all the way around once, and then on the second time stops at the same terminal side. So we've started at the same place, we've ended at the same place, but this angle is much larger than theta. In fact, it's the angle theta plus a full rotation around the origin, which is 360 degrees, or in the context of radians, this new angle is theta plus 2 pi radians. And these angles are different measures, but start at the same initial side, end at the same terminal side. Another example of coterminal angles, so those are positive coterminal angles. Another example is if we start at the same initial side, but if we rotate our angle the opposite direction, if we rotate clockwise, this angle is actually what we consider to be a negative angle because of the clockwise rotation. So clockwise rotation equals a negative angle. And so in this case, we started at the same initial side, ended at the same terminal side, but we've got a new angle that isn't theta, our original theta, and it's actually the difference between theta and a full rotation, which is 360 degrees again, or 2 pi radians. And actually these are just two examples of coterminal angles. You can probably see there's an infinite number of coterminal angles to angle theta, because if we've added a full rotation of 360 degrees, or we've subtracted a full rotation of 360 degrees, why not do 2 full rotations, or 3 full rotations, or 4 full rotations, or 5 full rotations? You get the idea. We could keep going around and around and around and decide to stop at the terminal side at any point. And so each one of those is a coterminal angle with theta.